Okay, so the first thing we need to do is understand a little bit about how these digital multimeters work. They are digital because they display digits. They are multimeters because you can measure many things: voltages, resistance, capacitance, current, and even temperature if you have a thermocouple. Okay, so the first thing I'm going to do is you all are going to get a really interesting lesson here. I've never seen this, and it's real easy, and everyone should do this. What I'm going to do is show you something about the intrinsic properties of digital multimeters. And what I'm going to do is I'm going to set one of them to measure resistance. That's this big omega, caps omega, the Greek symbol omega. And then I'm going to set this one on voltage, okay? So that voltage with the two lines, that's an AC voltage. So I've got it set on DC voltage. That's what we're going to measure today, DC voltages. But what I want to do is, this is really interesting. It'll tell you something about multimeters. I'm going to connect the commons together, and these are banana plugs. These are just homemade. It's got a speaker wire and two little banana plugs. I'm going to connect the commons together, and then I'm also going to put this in volt and put this in volt. I'm going to set this one to resistance. That's big omega, and I'm setting this one to voltage. So notice that the voltage and the resistance are measured in the same input. Now, this is what's interesting. I am measuring the resistance of this meter, the internal resistance. Notice how large it is. About 11.1, 11 mega ohm. Big M ohm. That omega is ohms for resistance. And resistance, by the way, is the opposition to current. Like an insulator would be have a very high resistance. A conductor would have a very low resistance. So the opposition to current. So when you are trying to measure voltage, the internal resistance of the meter is very high. Now, this is what's interesting. We are measuring the voltage of this. This is an ohm meter, so I've got it set up like this. This is a voltmeter, let's say. You're measuring voltage. And this is an ohm meter. I've got them configured that way. So notice what we see. We see, from this point of view, we see a very large resistance, internal resistance, at this setting. Also, we see when we set this to ohm, we are measuring about 1/4 of a volt, 0.23 volts. That's interesting. And we're going to come back to this later so you can really understand how to use multimeters. Now, watch this. I'm going to leave this one on resistance, and I'm going to take this out, and I'm going to set this to milliamps. That's 1,000th of an amp. That's a small amount of current. That's a very common quantity of current that you would measure. So I'm going to put this in the milliamp setting. Now watch what happens. We see that when you configure a multimeter to measure current, it has a very low internal resistance, only 2 ohms, about 2.2 ohms or so, 2.3 ohms. And notice that the ohm meter, a minute ago we saw that it was supplying about 1/4 of a volt. Now it's supplying about 0.2 milliamps, 0.2 milliamps. So when you're wanting to measure resistance, this acts like a power supply. And it's going to compare values that it measures with an internal resistance and calculates the resistance for you, okay? So that's what we want to do next. Okay, I hope you got that. That's really interesting. Okay, now, what we're going to do now is we're going to measure the resistance of different objects. And recall the video where I had a very brief, very, very elementary discussion about the electrical properties of conductors and insulators. So what I want to do is we're going to set this to resistance, and notice that when we're measuring right now, we're measuring the resistance of air between these two leads, and it's so big. That's OL, means overload. It's just huge. This meter will measure up to maybe 15 million ohms, so it's much, much bigger than 15. It's just huge. Like, this is an insulator, see? But if you hook the leads together, you should get close to 0. See that? Now, I will say this. This is not accurate at really low values. Anything below an ohm is just not accurate. You're just not getting any accuracy. And you also don't get really good accuracy, of course. All we know here is that the resistance is huge. Okay? But what we're doing when we do this is where we see that these wires are conductors. The inside of this insulation, this is rubber, but inside there is wire, and it's a conductor, very low resistance. See that? Now, let's look at an insulator. Here's a piece of foam. If I just pinch the insulator, obviously it's not a conductor. It's still overload, an insulator. Rubber band. What are you going to measure, you think? Right? It's going to be still overload. Just insulator. Piece of paper. Insulator. I've actually rewired old homes where they used to use paper for insulation on old wiring. Seems kind of dangerous. All right, here's a piece of cardboard, obviously. Okay, how about a piece of wood? Obviously, it's an insulator, right? Okay. And on and on and on. I'll do a piece of string. Here's some nylon string. Obviously, an insulator, right? Now, what is about insulators? Remember, the valence electrons are tightly bound to the parent nuclei, so it's got a high opposition to allowing current to flow. Now, let's look at some, of course, plastic would be an insulator too. Let's look at some conductors you might already know. Here's a galvanized nail. This is a nail you can use outside that won't rust easily. It's galvanized steel. So if we measure its resistance, we see that it is very small. In fact, obviously it can't be zero, but it's so small that we can't measure it. But it's continuity. It's a good conductor. Okay, now, by the way, these leads here, this is your banana, and this is an alligator or crocodile. All right, crocodile. All right, now, here's a piece of copper. That's a standard conductor used for wiring in your home. Look at that. There you go. In fact, this gauge wire, that looks like AWG12. When you run circuits in your house that are 20 amps, that's their typical wiring size right there. Okay, here's a piece of aluminum. That's a conductor, right? Conductor. You see zero, essentially zero. Okay, aluminum foil will obviously be zero. It's the same stuff. Paper clips, I don't know what kind of metal that is, but obviously it's going to be very low. Probably zero. Yes, indeed, it is zero. Conductor. How about some coins? Here's a penny. Now, we might measure something if it's real dirty and we don't get good contact. Nope, it's zero. There you go. A little bit of dirt. Well, nope, it's down to zero. A little bit. That's probably just a little bit of dirt on the. Here's a nickel. Good conductor, obviously. Now, let's do something more interesting. Fuses protect circuits, and how they do it, there's a little bitty wire inside there. So if a fuse is good, you should get continuity. With a good fuse, you should get 0 ohms. Now that fuse is blown, I think. I didn't see the wire inside there. It looks like it was blown. So you can check if a fuse is blown. See, what this does is it protects circuit elements. If you put this in series next to something you want to protect, and too much current goes through it, it'll burn it up. And these are cheap, and instead of burning up the device you're trying to protect, you burn this up. So let's see if this is a good fuse. I think it's blown. I don't see the wire, but it might be good. I can't see. I don't see too well. Okay, yeah, it's blown. Yeah, it's blown. You see that it's overload. It's an open circuit. It's like it's not connected. Okay, so how about a thumbtack? Let's measure it. It looks like it's definitely metal. I'd say it's 0. Definitely. I'll touch this end of it. As long as I don't touch the leads, right? There you go. Yeah, 0, of course. Now, how about a light bulb? Okay, here I know this is a good light bulb. I just went and got that out of our laundry room closet. You can see the filaments connected. So that should be near 0 resistance. So you touch here and down here. And we see that, whoa, is that sucker blown? No, it's not good. It's good. I'm not getting a good contact. There we go. See? That's a good light bulb. The filament is not burnt. But if the filament was burnt like this one, that's a little miniature bulb, right? If I try, I got to touch here, and see that little black strip right there? That's an insulator. So that little tip is one lead, and that's the other. So if I touch it like that, you see, that's a good one too. It's good. Okay, let's find a blown one. Oh well, maybe there's not one. Thought I had some blown ones. Anyway, I hope you get the idea that You know, digital multimeters are nice to have. You can check batteries. You can check whether or not you have continuity in a circuit. What we're doing here, continuity would be 0 ohms. Anyway, and we just established how to determine a conductor versus an insulator. Okay, that's all for this little segment.